this drawing is completed, the design engineer's signature guarantees that this part will fit, that it will perform its function, and that it will stand up to normal and sometimes not so normal wear and tear. This is how the design engineer visualizes the part. The drawing is merely a vehicle whereby he communicates his thoughts and specifications to those who are concerned with production. The drawing must be concise, complete, easy to read, and easy to understand. It must take into consideration the capabilities and limitations of the men, hand tools, and machine tools available for production jobs. For instance, this 1-inch bore must be concentric within 1/1000th of an inch to this diameter. According to this note. Without this note, the degree of required concentricity would be unknown, which might result in an unacceptable part. The engineer inserted the note because his calculations showed that the specified concentricity is necessary for correct functioning. But to accomplish the concentricity, a separate and rather expensive operation is required, as will be shown. This balancing of expense against performance is at the core of almost all engineering decisions. It requires knowledge of the factors behind the expense as well as the factors which affect performance. In order to understand the expense factors, the engineer must be familiar with the tools and processes which will be used to produce according to his drawings and specifications. This film will show some of the tools and machines used to produce a part according to this drawing. The material is specified as SAE 1018. The overall diameter is 10 to 20 thousandths less than 3 inches, which permits the use of standard 3-inch bar stock. A piece of bar stock is sawed off. The stock is delivered to the lathe operator together with the drawing and a job order. And mounted in the lathe headstock. The lathe turns the piece while the tool is fed against it, either by hand or with power. The speed selector of this lathe allows a wide range of spindle speeds, from 850 to 20 revolutions per minute. The spindle may be rotated clockwise or counterclockwise. The selection of speed and direction depends on the type of material, workpiece diameter, and type of cutting tool. A chart is used to determine the correct speed and feed. This tool bit is selected as the proper one for the first cut. It is clamped in the tool holder of the lathe and moved up through the workpiece. The feed dial of the lathe allows the machinist to move the tool bit to within 1/1000th of an inch of the desired depth. The primary object of this rough cut is to remove material as rapidly as possible. Lathe spindle RPM, tool bit, and tool feed have been selected for that purpose, and material is removed to approximate the desired shape of the part. The finish cut, which aims at the specified 1-inch diameter, is now made. The more critical the dimension, the oftener the lathe must be stopped for checking the measurement. Such stoppages take time, and therefore cost money. The engineer must know when the desired result justifies such cost. Here a neck is being machined using a specially ground tool bit. Another special tool bit is clamped in the tool holder for the purpose of cutting the thread. The lathe spindle RPM and the longitudinal tool feed are synchronized to produce the desired thread, 3/4 inch major diameter, 10 threads to the inch. Class 3 fit was specified. The machinist must therefore proceed with extreme caution, take small cuts, and stop the lathe frequently for checking, using a specially hardened and round gauge. All the preceding operations were performed in one lathe setup, but we now have to reverse the workpiece in order to bore the other end. A dial indicator has been mounted to bear against the outer surface. The drawing specifies a maximum of 1/1000th of an inch total indicated reading, TIR. So the workpiece is rotated by hand and the chuck adjusted until the specified concentricity has been found when the chuck is tightened. Now the 1-inch bore can be cut in the lathe within the specified concentricity. A special telescopic gauge is used to check this inside dimension. Then the face is machined. All operations which may conveniently be performed on a lathe have now been completed. Almost every workpiece requires one or several operations on a milling machine, which is one of the most versatile of machine tools. Basically, it consists of a spindle to turn the tool and a table to hold the workpiece. The table can be moved up or down, sideways, or back and forth by hand crank or by power. The cutting tool is secured to the spindle. It may be rotated in either direction. There are many different types and designs of milling cutters on the market. They are available in various angles, diameters, lengths, numbers of teeth, and materials designed for the many possible operations which may be performed on a milling machine. Our workpiece is lined up on the milling machine table and secured to it by means of a vise. In this setup on the milling machine, we plan to machine these flats and this keyway. This calculator gives the spindle RPM and the rate of feed of the workpiece. The flats are now being milled. During the rotation of the cutter, each tooth cuts a chip out of the workpiece until the entire flat has been machined. An end mill has now been mounted in the spindle, and the keyway is being milled. The next operation is machining this timing slot. The basic milling machine is generally used for machining flat surfaces, but this timing slot requires that the workpiece be fed along an arc against the cutting tool. This can be accomplished by attaching a rotary table to the milling machine table. The workpiece is secured to the rotary table and aligned with the center of the milling machine spindle. The milling machine table, with the rotary table and the workpiece, is then located in relation to the cutting tool for the specified arc radius. The rotary table is turned by a hand crank, and as it is rotated, the tool cuts the desired arc-shaped slot. The milling machine table with the workpiece may easily be relocated for drilling these holes, because in the present setup, the relationship between the workpiece center and the milling machine spindle center is known. The dimensions of the holes are specified here. There are 4 holes, one of which is counterbored and 1 countersunk. The locations of the holes are specified by these dimensions. This dial is attached to a lead screw. By turning the hand crank, the milling machine table with the workpiece may be located with relation to the cutting tool. The workpiece is now being located for drilling one of the holes. There are 3 dials, 3 lead screws, and 3 hand cranks on a milling machine for moving and locating the table in 3 directions. The workpiece has been located for one of the holes, and the drilling is now in progress. The part has been moved to a drill press, and 1 hole is being countersunk according to the drawing. This hole provides a seat for a flathead screw. This hole is being counterbored. Note the pilot guiding the counterbore. This hole provides a recess for a socket head screw. For this diameter, the engineer has specified a surface finish and tolerance which are beyond the capability of a normal lathe operation. The engineer has calculated that this specification is necessary for correct functioning of the part, but he must also realize that his specification will result in an additional and rather expensive grinding operation. The machinist must determine which grinding wheel to select for this particular operation. There are many to choose from, of different size, grit, abrasive, and bond. The selected grinding wheel is mounted on an arbor. Which is secured to the spindle of the grinding machine. The grinding wheel is dressed to eliminate runout. The workpiece is secured in a chuck and adjusted for concentricity, similar to the lathe operation just shown. Extreme care must be taken in adjustments and setup. Frequent stops are necessary to measure the workpiece to make sure that not too much material is removed. If this happens, the whole piece may have to be scrapped. Note the flow of coolant to dissipate the heat. The dimensions are so critical that the workpiece must be near room temperature when measured. A high degree of surface finish is specified for this flat surface, which necessitates a separate operation on a surface grinding machine. As in the previous operation, the proper grinding wheel must be selected and mounted on an arbor, which is secured in the spindle of the grinder. The grinding wheel is dressed to eliminate runout. Because most workpieces are of iron alloys, surface grinders are usually equipped with a magnetic chuck, which can be magnetized to hold or demagnetized to release the workpiece. The magnetic chuck with the workpiece is moved back and forth under the grinding wheel. At the same time, it moves away from or towards the operator until the entire work surface has passed under the grinding wheel. The difference between a machined surface on the left and a ground surface on the right is readily apparent. Our workpiece is now finished, but the work must be inspected. Some dimensions may be checked with a scale. Other dimensions require a vernier caliper. Critical dimensions require micrometers. What you have just seen is a series of typical machine shop operations, such as turning, grinding, and milling. Every year, improved machine tools are designed, tested, and produced, with even greater accuracy and reliability built into them to meet the ever-increasing demands for precision manufacture. The processes which were shown here are typical of currently used conventional production methods when few workpieces are involved, and this includes the majority of operations. But there are also many instances where larger numbers of units are required. In such cases, there may be opportunities to reduce the total cost of production by utilizing mechanized or automated methods. As an example, this Kearney and Trecker Milwaukee-Matic machine in operation. It is a flexible machining center capable of milling, drilling, reaming, boring, and tapping. It automatically locates and feeds each workpiece, and for each machining operation, the correct tool is automatically selected and inserted in the spindle, and the spindle RPM is changed. It should be noted that the machining operations proper are performed in the same manner as on previously shown conventional machines. As a first step to set up this machine for a new job, a process man analyzes the drawing and lists all operations necessary to produce parts in accordance with its specifications. Next, for each operation, he selects the proper cutting tool and determines the relative position of tool and workpiece, also the proper feed and speeds and type of coolant. Each of these items is assigned a code number, which is translated into holes punched into a tape. Milwaukee-matic is equipped with a built-in memory circuit which stores the information transmitted from the tape. All necessary items pertaining to each operation, such as location, tool change, speed, feed, and coolant, are automatically actuated and executed in the correct sequence and at the proper time. Upon completion of the setup work, the labor cost of machining each part using the Milwaukee-matic concept is considerably less than that of conventional methods. Furthermore, because the cycle repeats itself exactly for any number of units produced, the hazard of human error is virtually eliminated, with resulting lower scrap rate. In cases where repetitive orders are involved, all that is needed for the next lot is to reinsert the previously used tape, mount the required tools in the storage magazine, and furnish material. There are some cases where many thousands, even millions, of interchangeable parts are required, as for instance bearing caps for a series of automobile engines. In such cases, it may pay to engineer a special machine for the job. This casting is to be machined as one unit and then split into a set of bearing caps. This is a schematic drawing of a Kearney and Trecker transfer type machine, especially designed for machining the bearing caps. Castings are carried through 13 stations, and at each station, one or several machining operations are performed. This is a transfer type machine in operation. Notice the transfer mechanism for moving the castings from station to station and the synchronized motion of the machining heads and tools. This sawing operation is the final one in producing a matched set of completely machined bearing caps. The entire series of operations is automated. But regardless of which method of production is found most economical for any actual case, the part must be made according to a drawing, and the drawing must convey all necessary information to produce the part desired. All engineers who become involved in design, production, and evaluation of any kind must acquire a working knowledge of these principles. And that takes in the vast majority of all engineers.